only pull. And right now, let's assume that this angle is theta, and this angle is theta. Let's take the same angle right now. Well, they didn't have to be, right? Well, did they? That's an interesting question. Did they have to be the same angle? Let's assume they're not the same angle and see what happens. Make it alpha and theta. See what happens. So let's use, let's finish our drawing. So I'm going to write down the rest of the forces in the problem. I'm going to use T to represent the tension in the rope. Now, if I have different angles, there can be different tensions maybe. Let's go ahead and say this is T1 and this is T2. All T means is it's the magnitude of the force that the rope is exerting on the thing hanging on the end of it. So in this case, my assistant's here. One is right here. She's pulling. She's exerting a force on the rope. The rope is exerting a force on her. The rope exerts a force on her in this direction. She exerts a force on the rope in that direction, right? So if I'm writing the three-body diagram of the slug, what I'm interested in are the forces acting on the slug. So from T1 right here, is the force of the rope on the slug up to the left or down to the right? Who thinks up to the left? Who thinks down to the right? So it is up to the left. The force of the rope acting on the slug is pulling. The rope is pulling up to the left. So what I'm going to do is I'm going to draw it right here, and I'll call it T1. That's the magnitude of that force. I'm going to do the same thing on the other side and call it T2. What I might do, you don't have to, but what I might do to keep my head straight for the problems, I might indicate the angles on my three-body diagram. You don't have to do that, but I often like to, just so I don't make mistakes. Oh yeah, I define this to be alpha, and this is my theta, right? Just so I'm clear. But I want to make it really clear what forces are here. Now, do I include the net force on my three-body diagram? No, because if I did that, I would be double counting. I've already got the other forces in the problem. Actually, so when they were holding the slug up, and it was, let's say it was holding perfectly still for a little bit, what was the net force going to be? If you use Newton's second law, what's the net force going to be? It's going to be 0. So these have to all balance out, right? So that means if you use Newton's second law, and we do it, let's define our axes. Let's define this to be the x-axis and make this the y-axis, and let's center the axis around the slug. But it doesn't matter. Really, what matters is the directions. But just for the sake of argument, we'll put the origin right at the center of mass of the slug. We haven't used the notion of center of mass yet in this class. We'll just say the center of the slug. All right. So then let's see. Newton's second law. All right. Let's do it in the x direction. Okay. Well, what is the net force in the x direction? Equals ma in the x direction. Okay. What is the net force? Well, it has three components. I've got the force of gravity in the x direction. I've got the force from T1 in the x direction. I've got the force of T2 in the x direction equals ma. I'm being really pedantic. I'm not even allowed. So each of these in principle can contribute. But what is the x component of the force of gravity? 0. So 0 plus. Okay. Now T1. All right. Great. So I've got my angle theta. Well, I've got to break this into components, right? And I drew it at a 45-degree angle, but I want to make my life easy. When I make my picture, I'm going to choose to make my angle alpha less than 45 degrees just so I can eyeball the components, right? Well, and actually it won't matter. I'm not going to draw a separate triangle for this problem, so it won't matter so much, but just to be happy. So if this is T1, what is the x component going to be, sine or cosine? Cosine. T1 cosine of alpha. Great. So that means I put in, is it positive or negative? Yeah, it's really important. It's negative, right? Because the force itself points up to the left. I define my x-axis to point to the right. So the projection of that force down the x-axis is pointing to the left, pointing in the negative direction. So I better get a minus sign for this. T1 is the magnitude times cos alpha, right, that's my magnitude. Good. And then I need this part over here. Well, same geometry over here, except it's theta instead of alpha, and you flip the triangle around. Now you get T2 cosine of theta. Does anyone agree with that? It's positive because it points mostly to the right, not to the left. It's T2 because it's the other magnitude of the other guy. And it's cosine because it's the adjacent, not the opposite. Great. I think that's all correct. That equals ma. Oh yeah, what is ma? What is ax? What is the x component of the acceleration of the slug? 0. So now I get an equation that says this has to equal this. So that's interesting. If we made the tensions different in the two ropes, we could handle the fact that the cosines are different, that the angles are different, right? But if we know that the tensions are the same, then alpha has to equal theta, right? If it's not accelerating, if it's 0 over here. And likewise, if we know that the angles are the same, then we know that the tensions have to be the same if it's not accelerating. Okay, so let's proceed assuming that all these things are the same. So alpha and theta are the same, and T1 equals T2. So that means that if we do that, if T1 equals T2, yeah, and alpha equals theta, okay, then when all this settles, we say, okay, that just says 0 equals 0, so you're fine. So the next question is, until that satisfies that equation, about the y direction. So this is really the business direction. This is the, when you're lifting something up against gravity, right? Gravity provides a vertical force. So it's only the vertical component of the tension in the rope that's actually holding that mass up, right? So how does that depend on theta? Well, if you write down Newton's second law for the y direction, we'd say that F net y equals ma y, and if you write it out, we'd say, oh yeah, so it's the same equation again. What is this? What is the y component of the force of gravity? Well, first of all, is it positive or negative given my convention? It's negative. Negative mg, right? Now we're going to add the vertical component to these guys. So that's going to be sine of theta. I'm going to try to make our thetas the same to make our life easy. All right, so I say, okay, now we add, well, notice this is going to be the same contribution here as here, right? You're going to get the same contribution from both. If alpha equals theta, T1 equals T2. So you're going to get 2 times T1 times, or we'll just call it T because they're the same. 2 times T times sine of our angle theta, and that equals mass times the y component of the acceleration. What is the y component of the acceleration if the slug's holding still the whole time? 0. So that means that these have to be equal. So if I put this on either side of the equation, I get mg equals 2 times T sine theta. And if I say, all right, then how does the tension depend on theta? Well, the smaller theta is. So, and I asked them to step further away from the slug, right? They further away. Well, if they don't change height, and they didn't, right? And if the slug is still the same distance above the ground, that means the vertical component of this rope is the same, but the horizontal component getting bigger, right? So theta is going down. The theta is going down, down, down. The further away they go. Theta is going down. Smaller theta. Did it get easier for them or harder for them for smaller theta? Harder. So that means that I'm expecting T to go up when theta goes down. And in fact, that's what happens, right? If I isolate, let's see how big is, let's go this way on the board. Let's see how big is the tension have to be? How hard do I have to pull? Well, it's equal to mg. So the bigger mg is the bigger tension has to be. That makes sense. A heavier mass, more mass means bigger tension you have to provide, right? And then we divide by 2 because there's 2 people pulling. So that's how does it work? They're having to pull half as hard as they would if they were doing it by themselves, just on one side. Although that's not symmetrical, it's kind of strange to think about. Well, yeah, okay. So what's the final thing then? Oh yeah, sine theta. And that goes from top to bottom. And remember that. See if I got that. Oh, is that right? Yeah, that's right. Good. Remember that sine theta. When you let theta go really small, go to 0. Sine theta itself goes to 0, right? Sine theta, right? So for small theta, you get small sine theta, right? In fact, for very small angles, you're going to approximate that with unity. Sine theta is approximately equal to theta for small theta, which we'll use later in the semester a lot. However, if you do this, remember this isn't true for degrees; it's only true for radians. Who here does not know what I mean when I say radians? Everybody knows what that means. Good. Yeah. So you have to use radians, not degrees, for this equation to be exactly right. Otherwise, you need some proportionality constant in front of it. Yeah. Okay. Small angle approximation. So the point is that yes, tension, this equation seems reasonable because tension goes up when theta goes down. Yes, that's right. Because theta goes down, sin theta goes down, whenever sin theta goes up. And if I check the units on this equation, I'd say, well, what's the units of t? What unit should that be in? Yeah, it's newtons. It's units of force. It's kilograms, meters per second squared. Well, that's what I've got right here, right? This is kilograms. That's meters per second squared. The denominator 2 has no units. Sine of theta's got no units. So good. I've got units of the force. So that is reassuring. At least I can't prove it's wrong, right? It's like it's right. Yeah, good. So that's what's going on. What about this situation? Suppose I've got this situation. I've got the ceiling, I'm hanging a rope. I've got some block hanging on here. What's the tension in this rope if there's this block hanging here? Yeah, it's just going to be mg. Tension here is going to be mg. What about this situation? And so what you did right there is you used Newton's second law and said, oh yeah, there's a downward force of mg. Must be an upward force to the rope of equal and opposite. Otherwise, this thing would be accelerating. Suppose you got a block hanging there and a block hanging there. Are the tensions here the same? Is T1 equal to T2? Is T1 bigger than T2 or is T1 smaller than T2? Yeah, think about that a little bit. So here's another question. We've been doing all this stuff talking about a solid block, and I told you at the very beginning that we're going to be thinking about these. I'll actually talk about that more next time. We'll talk about that. But think about it. Figure out what the answer is. T1 bigger or smaller than T2? We can use Newton's second law and Newton's third law even when we have systems of objects. And it's worth thinking this through. So suppose we got, so the canonical example, the book has an example of the horse drawing cart. So if you've got a cart, right, it's on the ground, right? So you've got some cart, and it's, all right, whatever it is, basket's full of hay, whatever it's got, right? So you've got some cart, and it's being pulled by a horse. So this is a pretty complicated system. Depending on what part we're going to focus on, right, we may have to decide whether or not we're going to focus on the horse as a separate object, or whether we're going to think of the cart as a separate object, or whether we're going to think of the whole system, right? Right? All right. Here's the little horse. Oh, he's got a big mouth, that's okay. It's more of a donkey. Oh, we got a donkey. He's got a donkey. Oh, okay. All right. That's more applause than I got for this demo. I'm gonna stop doing this demo. Okay, so you have a horse, right? So if you have a horse, and he wants to pull the cart. So how can this, he's kind of stumpy, but how can this horse pull the cart? What forces are in the problem? There's a lot of forces in this problem. I drew it only with 2 wheels on the cart, so at least there's only 2 points of contact. The horse has 4 points of contact with the ground. And there's forces between the two. There's also forces within the horse, like his head pulling on his neck and his neck pulling on, right? All this stuff. So when you make a free body diagram, we implicitly do this. Let me be really explicit about it. We make free body diagrams, we don't include all the internal forces. We're only including external forces. Like in this case of the slug, right? We included the force of gravity, we included the force from this rope, the force from this rope. But we didn't include, say, the force that this part of the slug is exerting to hold the part below it on, right? Like there's all kinds of forces inside the slug, otherwise it would fall apart, right? But we ignore those. Why? Because they're not going to change the equation. We know from Newton's third law that any internal force within the horse or within the slug or within my body or whatever it is opposed by an equal and opposite force acting the other way around, from that bone onto that muscle as opposed to the force from the muscle to the bone. Those opposing forces, right, wind up those opposing forces, right, would cancel out if we included them both in Newton's second law. When we write down the net force, they would just cancel out. So we don't bother to include all of them, right? And you've got 2 objects in a problem, and you're asked to find something. You have a choice to make about what you're going to consider the system to be. Is this the system, right? Is this the system, or is this the system, right? And you'll get different. Well, you'll get the same final answer. The question is, what's the force of friction acting on the hoof of the horse? You're going to get the same answer, but your equations along the way will look different depending on what you choose for your system. So in this case, let's think about all the forces in the problem. For one thing, there's normal forces here. There's 2 wheels, right? What I often will choose to do with a problem that's got a car in it or a horse or something, I'll often say, well, let's just consider all the normal forces as one force. You can get away with that at this stage in the class. You won't be able to get away with that later when we talk about torque. Like if there's a big force here, a small force over here, the object will need to rotate as a result of torque has to do with forces that result in the rotation of things, right? So right now I'm worried about torque. So I'll say, okay, let's just call a single normal force. So and I'll use a different color. Again, I apologize to anyone's colorblind, but just so there's a lot of stuff on this graph. So I'll say, all right, well there's a normal force here, and we often just say F sub n to be normal force. But in this problem, maybe I better put more labels on. I'll say it's the normal force of ground on cart, and I can draw a downward force here. That's a normal force, but that's cart on ground. Right? You can't read. It's not real clear, but let me write it. Cart on ground. Right? And then I've got this cart is exerting also you have a choice. Are you going to include this bar? You've got some fancy, whatever the heck it is, some crazy harness on the horse or something. Are you going to, like, what force are you talking about? Well, we can just sort of lump all this stuff together into the horse and say, let's consider this rope as starting right here, say. So there's a rope right here, it's got some tension T. And so there's a force right here of the rope acting on the cart. That points that way. So that's T, and that's acting, on the cart, right? But then there's a force like this, right? That's the force of the cart on the rope. What else do you have? You have gravity acting down on this guy, right? Gravity acts down. M cart times G. There's M. There's the force of gravity, which is m of the horse times g, right? And again, I'm just lumping all the forces. Gravity's actually acting everywhere on this horse, right? But I talk about it as though it's just one object and I just have one force. That's perfectly legitimate, and you can prove it mathematically. But we sort of do it implicitly in this class. Otherwise, we couldn't handle anything, right? If you had to actually deal with all the forces acting everywhere on the horse, we'd be sunk, right? It'd be too complicated. There's no way we're going to do the integral of that funny shaped horse, right? It's impossible. So thank goodness we can actually get the right answer by including all the force of gravity acting everywhere on the horse, as so disturbing. Okay, so what else do we have? Oh yeah, and then there's forces over here. There's the force, there's the force of the rope on the horse. Then there's this way the force of the horse on the rope. And and then let's just lump them all together. One normal force that's from the ground on horse, and similarly the other way around. Normal force of horse on ground. Okay, and so I'm missing something because what's going on here is let's say the horse is just starting off, right? He's starting off, they're pulling the cart, going that way, starting from rest, so there's some acceleration in the problem. Everything's starting to accelerate. Where is that force in this problem? Because right now I've got these equal and opposite forces here. I've got equal and opposite forces here. They cancel out. Now here I don't have equal and opposite forces from I got, let's see how I say it. Well, these are equal and opposite. Let me draw this more carefully. The downward force of the gravity on the cart is equal and opposite to the upward normal force on the cart. Those cancel out. This force here is acting on the cart, it's acting on the ground. So I don't include this when I do my Newton's second law for the cart. Let's see. But I do have, well, let's see. So as I've drawn it, there is a net force acting on the cart, right? Because this guy pointing to the side is not being balanced by anything. But what about the horse? So in the horse's case, there's a backward force through the rope, but the horse is moving forward. So what other force do I need in the problem to account for why the horse is going to be accelerating forward? I've got normal forces on the ground. What do I need in addition to that? So suppose I have roller skates on, right? It's a sort of funny image. And I'm facing this way, and I start trying to take off. I'm not moving, right? So why? I have a normal force. What else do I need? Force of friction. I need a force of friction. And so, sure enough, the reason a horse can pull a cart is that the ground can exert a frictional force on the horse. Which way is it pointing? To the right or the left on the horse? If it's pointing to the left on the horse, then the horse will accelerate backwards. So it must be that the force of friction from the ground on the horse is pointing this way. Force of friction. Did I say that the right way? Force of friction, ground on horse. Now the horse is exerting, by Newton's third law, an equal and opposite force on the ground, a frictional force. And that points to the left. And but that's not acting on the horse, that's acting on the ground. So that's a force of friction, and it's force on ground. Yeah, so that's how it is that the horse can actually accelerate forward, and how it is that ultimately the cart also accelerates forward. Of course, the reason the cart's accelerating forward is that the rope's pulling on it, right? There's a net force in that direction. It's not being canceled out by the gravity force or the force of the normal force. Oh, I should point out, too, I drew this rope is angled upward a little bit. So the force on the cart from the rope is a little bit up like that. But if the cart's not leaving the ground, right, if it's staying on the ground, that just means that the vertical components of this force must be balanced out a little bit by the net force between the downward force of gravity and the upward force due to the normal force. In other words, the force of gravity down on the cart is a little bit bigger than the upward normal force on the cart. Right? After all, if what I do is I pull on this rope right here, so I pull up a little bit, not enough so that the thing leaves the ground, that means I'm lowering the normal force that's acting from the ground on the slug. Right? Because I'm providing some upward force because of the rope on the slug. So that means that the downward force of gravity is bigger than the normal force while I'm pulling up a little bit. But if you add together the normal force, the force due to tension in the rope, the upward force in the rope, you add that to the normal force from the ground, that adds up to the force of gravity downward on the slug. It must. The net force is zero. It's not accelerating. Right? The same thing is true here, but it's a little trickier because it's not vertical rope. It's in an angle. But that's okay. Just break it into components. Make an X direction and a Y direction. The vertical component of the rope's force added to the upward force, the upward normal force from the ground on the wheel of the cart, those had better add up to the downward force of gravity on the cart because it's not accelerating in the upward and downward direction. It's only going that way. Right? Yeah. So anyway, so it's worth when you make free body diagrams, and when you do Newton's second law, you got to think clearly about what is the system I'm talking about. And if your system is just the horse, then the force from this rope acting on the horse is an external force. You better include that in your free body diagram. If your system consists of this whole system like this, with the cart and the horse, then you better not include these internal forces, because given the system you chose, these forces aren't they're internal. They're just going to cancel each other out. So you leave them out. All right. So there's a little more forces on Thursday. See you soon. Oh, and no office hours tomorrow or today for me. I'm not going to be around for those. Next week I get back to normal office hours.